I'm actually not working on the thermal instability, but rather on this topic, which is the excitation which is the excitation of inertial acoustic waves in turbulent accretion disks, and I'm doing this work together with my PhD supervisor, John Papaloizou. Now here's a cartoon of an accretion disk, and in this accretion flow, balance between centrifugal force and gravity leads to a rotation law where the angular frequency omega depends on radius. So there's differential rotation, and because there's differential rotation, there's also shear. Wherever there's shear, there's a good chance that there will be turbulence as well. Now, and indeed, at least if such an accretion disk is sufficiently magnetized, then the magnetic rotation instability kicks in and produces turbulence very efficiently, or at least, well, it produces turbulence. And this is good news because it explains why accretion disks actually accrete on timescales that are shorter than the age of the universe. And but it's sort of bad news because turbulence is a very hard problem, as I'm sure you know. And but nevertheless, one can try to study this turbulence, the turbulent properties, and a very useful model for studying the local properties of this turbulence is the so-called shearing sheet approximation. Now, in this approximation, one considers little boxes, little square boxes that are orbiting around the black hole here, or whatever there is in the middle, and they orbit at the local angular frequency, which in general, which I assume is given by a power law dependence on radius. For Keplerian shear, Q is 3/2. Now, in this little boxes, you adopt a Cartesian coordinate system given by these identifications, and because there's differential rotation, the differential rotation globally is represented locally by a linear shear, which depends on the rate of change of the angular velocity, angular frequency, and the frequency itself. Now, the equations to solve in this system are given, I've written here. There are a number of assumptions that went into this set of equations. First of all, I use an isothermal equation of state, which is very simple. And I assume that the box is very close to the midplane, so that I can forget about vertical gravity. And so what I'm left with is the Coriolis force, some stretching terms due to the shear, and advection terms in all of the evolution equations that result from advection by the linear shear, by the steady state solution. Now I've defined here, which somewhat strangely, the linear momentum P, bold P, rather than P, which usually means pressure. This is bold P, this is linear momentum, which is rho times the velocity. Will, in this problem, turn out to be advantageous to work in terms of momentum rather than velocity. And angular frequency is given by this. And all the nonlinear terms have bunched together in the nonlinear stress tensor, which appears as the divergence, as a divergence in the momentum equation, and it's given by this. So I include which includes the magnetic field and everything, and the Maxwell and Reynolds stresses. Now the question is, in the shearing sheet where you have advection by the linear shear, what kind of boundary conditions can you are these equations subject to? Now, since there are not really any walls in an accretion disk, one ideally likes to use periodic boundary conditions. So, which would be can be imagined like this situation where you have, this is your computational domain, and you have sort of infinite many replicas of the computational domain in all directions right next to it. But because they are shear, the way to think about periodicity is in fact like this, where you have, where the infinitely many replicas shear with respect to the computational domain you're actually in. And so what would be appropriate here is to not use strictly periodic boundary conditions, but shearing periodic boundary conditions that, well, I hope it's clear what you use. So these red dots are actually the same. So you have a time-dependent boundary condition. in this problem. And this kind of boundary condition makes sense because if you, that was not the slide. Okay, so well, okay, so this is how the boundary condition actually looks like if you write it down. Now, this has important, because you're not strictly periodic but shearing periodic, as it's called, that has consequences if you want to do a harmonic analysis in the shearing sheet. And that has to be modified. And what you have to use is a time-dependent Fourier basis, given by this, where the radial wave number actually explicitly depends on time, and it depends on time linearly, and the time dependence is actually given by this. So it also depends on the azimuthal wave number ky. And now, the way to picture the evolution of one Fourier mode in the shearing sheet is that it starts out in the infinite past with, you see, if q and omega are positive, then it starts out in the infinite path with kx over ky is negative, and that's called the leading phase. And then it goes through a point where the radial wave number becomes 0, and then in the infinite future, it ends up as it's leading, then the radial wave number becomes 0, and then it's trailing, and it eventually ends up, so it always ends up as a trailing mode in the infinite future. It's a tightly wound, wrapped leading mode. Okay, so now the fact that the radial wave number depends on time makes sense, because if you consider the advection of sort of a sinusoidal disturbance in the shearing sheet, it looks like this, yeah, and you want to allow this to happen. You want disturbances, sort of shear disturbances, to be advected by the linear shear, by the mean shear, which is illustrated here. So, I mean, this is not the same wave. This goes on. This is a new wave now. And you see here that what you want to do is have time-dependent periodic boundary conditions so that these points are always identified. Yeah. Right, and so now the wave is leading, swings through 0, and now it's trailing. Yeah. So this is the evolution of Fourier modes, and how to think of the evolution of Fourier modes. Right. Okay. So so in the shearing box now, which is 3D, one can do numerical simulations and of MRI turbulence. And this is a simulation that I've done with the Pensacola for the Heinemann et al. Paper earlier this year. I have a box which extends one scale height both radially and vertically. Now, scale height this is not stratified, so scale height is sort of funny to talk about a scale height. Here it's just the sound speed over the angular frequency, which is called h in this case. And the extent in the azimuthal direction is 4 times longer, so it's 4h. And there's the background state is uniform density, just random noise in the velocity field, and then a weak magnetic seed field, a weak magnetic zero net flux, which is sort of important, magnetic field, which varies sinusoidally in radius. And the Prandtl number, so from et al. Showed that the turbulent transport properties sort of critically depend on the magnetic Prandtl number. The Prandtl number I chose here is 4, in which you observed sustained turbulence for many hundreds of orbits. And what that looks like is, so this is magnetic field strength, it's like this. So it takes a while until the MRI kicks in. It's going to be a channel mode, hopefully soon. Yeah, now it's kicking in. And then axisymmetric disturbances set in, so secondary instabilities, and the whole thing breaks up into what's usually what one might call MRI turbulence. And you see that all the turbulent features sort of elongated in the azimuthal direction, which is why one usually chooses the azimuthal extent that is sort of longer than the other directions. And by the way, this conversion, it looks like things are converging towards the x equals 0. That's just a visual sort of effect, because you have these sheared structures that are advected in this direction, and so if it's a projection issue. Okay, right. So so on the lower panel, this is alpha. You can get a value between 5 times 10 to the minus 3 and 10 to the minus 2. And in the upper panel, you can see that this is actually strongly subsonic turbulence. This is in units of the sound speed, which I should have put there. But even though the turbulence is subsonic, if you look at the density field, it looks like this. Yeah, you see wavefront. The color table isn't very good, I'm afraid, but you see these wavefronts propagating in the horizontal plane, and sort of slightly inclined towards the with respect to the azimuthal axis, but very little in the vertical direction. Yeah. So let me integrate over z. Then the picture looks like this. So you see that there's a characteristic angle these wavefronts have with the azimuthal axis. This actually means that we're dealing with trailing waves here. They're all trailing, and you can see the waves in density and velocity. You don't really observe these waves in magnetic field, though. These are purely hydrodynamic waves. And so what I like to find out is what these waves are about. And by the way, yeah, so you get density fluctuations of about up to 30%, which you wouldn't expect usually from a strongly subsonic flow, but they are actually up to 30%. So I'd like to find out what these waves are about. It has been speculated that maybe they're an artifact of the shearing periodic boundary conditions, and I want to find out whether there's a mathematical way of describing them.
It appears that it's just a 1 to 4 slope in the. Is that not true?
Right. Yeah. So.
Sorry. Go ahead.
No. So.
Is that just my eye picking out that?
No. It is. That's exactly what it is. So it's on the longest azimuthal wave number and sort of longest radial wave number as well. These waves. Yeah.
So if you took
it's box dependent.
Yeah. If you took 8.
If I take 8, it's still on the longest. The power peaks on the longest wavelength. If I pick 16, then it's the second longest. So there's some saturation apparently. Right. But 16 is sort of difficult to show in a movie because it's
Too thick.
right. So okay. So and you can what you can do. You can do a Fourier analysis of this thing. You can Fourier analyze these sort of vertical averages. And bear in mind that this is a time-dependent Fourier series where the waveform depends on k. And if you do this, it looks like this. So this is a single shearing wave, as observed in the simulation, computed via an FFT that I've done during the simulation. And what's plotted here is simply the real part. I think I don't know why I didn't put a title there, but this is probably the real part of the density amplitude as a function of radial wave number and thus time, because the radial wave number just depends linearly on time. And what you see is that there's really nothing. So there's nothing basically in the. So this is the leading phase. So there are no waves. No excitation occurs in the leading waves, but then as the mode swings through zero, when kx becomes 0, there's the excitation suddenly occurs, it's amplified, and then it decays. Yeah? So what this means is that what you see here is not just one wave; it's just actually a succession of waves. Yeah? It's sort of trailing waves come in, get excited, dissipate, and then the next one comes in, gets excited, and dissipates. Yeah? So this is what you actually observe. I think.
What's the dissipation mechanism?
Well, I haven't really investigated. I'm going to comment on this briefly later. Well, I'm going to do a linear theory in which the dissipation mechanism cannot capture, unfortunately. Right. So this is what it looks like. Now, so ideally you would like to. So what I'm going to do is I'm going to derive a wave equation that these waves obey. Yeah? So these are the equations that I showed earlier. Now I've defined this vector n, which is just the divergence of the nonlinear terms. And then if you go to Fourier space, equations look like this. Yeah. So the advection terms are sort of disappear, but instead at a cost of having a radial time-dependent radial wave number. So these are the equations you. How they look in Fourier space. If you then differentiate the py equation with respect to time, and you shuffle terms around, what you get is this, yeah, this equation. So you have a harmonic oscillator on the left-hand side with a sort of acoustic frequency bit and an inertial frequency bit, which is why I call them, or they are called inertial acoustic waves. And then on the right-hand side you have sources. Now these sources come in two different types. First of all, there are the nonlinear terms, nonlinear source terms, which are complicated. But then there is this term, yes, which involves psi z. I should have called it zeta z, but never mind. Which I call the pseudo potential vorticity, or PPV for short. Mostly in lack of a better name. If anybody has a good suggestion what to call this thing, then I'd be very keen on.
Why pseudo? Why pseudo?
Well, because it's actually not potential vorticity, as in Gammy and Johnson, I think. They also show that you have this linearly conserved quantity, or even non-linearly, in the shearing sheet, which is basically vorticity plus an inertial bit. But this is not the same. So don't really know. So I call it pseudo potential vorticity for now. And I like PPV, but anyway. So
what is C in that term?
C.
Sound speed, yeah.
Oh, this is the sound speed, yeah.
Oh, so the C on the right hand side is the same as the.
Oh, sorry, yeah. There's an S here. There's no S here, but they're the same. I'm sorry. Right. So okay. So the potential vorticity is like defined like this. So it's like the curl of the momentum plus some term involving omega and rho. And so the important thing about this quantity is that it only varies non-linearly in time. To linear order, it's conserved. It's a conserved quantity, yeah, for one wave. Right. And so what I'm going to do is do a quasi-linear analysis in the sense that I forget about all the non-linear terms, and just assume that there is some. So all the effect the non-linear terms have is to generate some potential vorticity. And when the excitation occurs,